right. Oh, yeah, okay. So what we're talking about today is we're going to talk about diagonalization of matrices, which I asked you to do on your worksheet last time, but didn't tell you how to do it. So this time I'll tell you how to do it. So there's going to be 2 days on this, and part of tomorrow I'm hoping is I can show you guys about once we've got sort of our idea of what diagonalization is up and running, I can show you the Google PageRank thing, like how Google made all its money, right? At least in part. With very high-level computer science coupled together with very easy linear algebra. All right, so this is called diagonalization. And so first, I'm going to walk you through, I'm going to remind you what a diagonal matrix is and some good properties of diagonal matrices. Then I'm going to make the argument that there's a whole class of problems that would be easy if we could turn matrices into diagonal matrices, and then I'll show you how to do it. So recall, a diagonal matrix is an n by n matrix with all non-zero entries on what's called the main diagonal. Just to say, it's a matrix D that looks like A11, A22, A33, down to ANN, and every other entry must be 0. These could be 0, but if anything is non-zero, it has to be on this main diagonal, and every other entry is 0. And because the zeros aren't really giving us a lot of information, it's common when we're writing diagonal matrices just to write the diagonal entries and then just leave all the rest of it out. The book likes this notation for diagonal matrices. It says diag A11, A22, up to ANN. So it tells you the elements that are supposed to be on the diagonal and then leaves it to you to construct the matrix. So for example, if I have the matrix D is equal to diag -1, 2, 6. I could write that as -1, 0, 0, 0, 2, 0, 0, 0, 6. It's just notation, so I don't have to write an entire matrix every time I want to write down a diagonal matrix. Okay. So diagonal matrices have a lot of properties that make them really conducive to doing calculations. So a problem that shows up frequently in applications is I might need to take large powers of a matrix. So if I give you a matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9, and I ask you to take the 100th power of that, that's a hard problem. Now, you might ask, reasonably, like why you would ever have to do something like this. The answer is there's a lot of problems that are studied in application that I can think of as a system, and then it evolves as time goes along, but in the same way each time. And so the state at the beginning might be a vector v, and after 1 time step, I multiply by a once. And for 2 time steps, I multiply by a twice, and so on. This is called dynamical systems. This is actually going to be used when I show you guys the Google PageRank thing. So this is a hard problem. Lots and lots and lots of multiplications to do here. Hundreds of multiplications, and it scales terribly with the size of the matrix. The bigger the matrices are, the worse this gets. In fact, generally the difficulty of working with matrices isn't the mathematical setup, it's that numerically, the amount of information you need to start storing when the matrices get big is ridiculous. They're hard to work with. And so any reduction in complexity that we can get is really important. If I gave you a different kind of matrix, this is not related to this matrix at all, just another example. If instead I gave you this diagonal matrix, maybe the one from above here, and I took that matrix to the 100th power, that's easy. A diagonal matrix, I just put the powers inside. So diagonal matrices are easy to take powers of. You do what you want to do, right? Oh, well, the power you can't just put the 100 on the inside of this matrix. If you think you can, you should test and see. So diagonal matrices are very easy to take large powers of. Okay. Another example. of the sorts of things we can do with diagonal matrices, or that diagonal matrices make really easy. If you imagine that you had, say, a system of differential equations of the form x prime is equal to, say, a times x. And what I mean here is x1 prime, x2 prime is equal to a11, a12, a21, a22, x1, x2. If you multiply this out, you end up with a system of equations. X1 prime is a11 x1 plus a12 x2, and then x2 prime is a21 x1 plus a22 x2. I've described this type of model to you guys with that fox and rabbits model, where you have population growth depending on, two different populations are contributing to the growth of population one. Because each of these differential equations involves both variables that are changing, this is called a coupled equation. x1 prime depends on x1 and x2. I can't just integrate this to get the answer because it depends on a variable that I don't know the integral of. I can't integrate this. I mean, if it just looked like that, that would be something that we studied at the very beginning of the class. Y prime is equal to cy. That's an easy differential equation to solve. When I put this extra variable in here, it's not. So if the A is not diagonal, you end up with what's called a coupled differential equation, which means you can't just integrate it. On the other hand, if I gave you a setup like that and the matrix was diagonal, so if I gave you a different system, like, I don't know, y1 prime, y2 prime was equal to 1, 0, 0, 2, y1, y2, where now this is diagonal. If that was a diagonal matrix and you multiply this out, you get y1 prime is equal to y1, and y2 prime is equal to 2y2. I could just eyeball the solutions to that. I could use separation of variables, or I could just look at it and say, I know a function that's equal to its own derivative. It's e to the x. I know another function that's equal to, whose derivative is twice the original function. It's e to the 2x. I could just read off the answers. I can integrate here. I can integrate. This question, this set of equations is not coupled, because the differential equation for y1 only has y1s in it, and the differential equation for y2 only has y2s. So if I had started with a diagonal matrix, I get something I can use easy techniques to solve. If I have something where it's not diagonal, it's basically impossible. Yep. That is the whole point of chapter 7.3. If only there was a way that I could take a non-diagonal matrix and make it into a diagonal one through the process of diagonalization. So that's kind of what we're driving. So we're going to do some definitions at the beginning, and I'm going to show you how to diagonalize matrices. Yep.
But this doesn't work for eigenvectors, right? You can't diagonalize it.
Just.
Well, the other one, you said the other one didn't work when I was doing it for the test.
Yeah, just wait. I'll show you. You're pointing at issues that are going to come up.
Oh, sorry.
I promise. Like, I'm going to talk about all of this. If your questions still aren't answered when I'm done sort of describing things, just keep poking away. The stuff that we're doing here is really important, and also like even more definitions on top of the rest of them. Okay, so we're going to start with a notion called similarity. So two matrices of the same size A and B are said to be similar if there is an invertible matrix S with B is equal to S inverse AS. And specifically, we would say here, A is similar to B. A is similar to B if I can find an invertible matrix S that sort of B arises by taking A and pre and post multiplying by S and S inverse. Now, I don't have the time in this class to go through the theory of what that represents, but I can tell you in words, and I'll point you to a resource to look at. You should think about what these matrices are doing as change of coordinates. From like 241 when we did the change of coordinates theorems, right? Or if you didn't take 241 with me or you haven't done multivariate calculus, you can also think about this as being kind of related to a U substitution. What we're saying is two matrices are similar to each other if this matrix looks like change coordinate systems, do A, and then unchanged coordinate systems. That's basically what the picture is here. If you want to see this in more detail, I highly recommend either dropping this class and going to go take at like 206, or you could look at, there's a sequence of really nice videos at 3 Blue, 1 Brown called The Essence of Linear Algebra. I don't know about you guys, but I love sitting around and watching dorky videos on YouTube, right? So like if you want to like see like a description of what's actually happening here, he's got some really nice like visuals about what this really represents. Unfortunately, because I have the time that I've got, we're just going to say this is a thing called similarity. It represents two things that are the same if essentially you change coordinate systems to get from one to the other. All right. So, I guess what we want to say here is we're interested in looking at matrices that are similar to diagonal matrices. So, let's suppose for a second that a matrix A is similar to a diagonal matrix. And suppose I wanted to calculate something like A to the third. I'm only choosing a small power here because I want to make this completely clear what's happening. So the first thing we're going to write down is, if A is similar to a diagonal matrix, that means that S inverse AS is equal to the diagonal matrix D. That's what it means for A to be similar to a diagonal matrix. And I want to replace A with an expression that has diagonal matrices in it. So I could rewrite this expression as A is equal to, well, if I multiply both sides on the left by S and both sides on the right by S inverse, I could turn this equation into this one. And the idea here is, if you wrote down A to the third and you replaced A with S ds inverse to the third, taking some to the third power means writing it 3 times in a row. S ds inverse, S ds inverse, S ds inverse. What happens to the S inverses and the S's that are touching each other? They go away. They're the identity matrix, right? So you could think about this as being S times D. These guys cancel into the identity. Then there's another D. These guys cancel into the identity. Then there's another D. And then there's an S inverse. But what does the identity matrix do to a matrix? It just leaves it alone. S D D D S inverse, which is S D to the third S inverse. And diagonal matrices are easy to take powers of. If I could figure out a way, if A was similar to a diagonal matrix, then powers of A can be computed by taking powers of a diagonal matrix. So I'll be more concrete with that.
Is there any way, though, that the S's can make the D not a diagonal matrix anymore?
Well, what will happen is the diagonal matrix D you'll take a power of, and then when you do the coordinate change matrices, it will suddenly become not diagonal again. Right? That actually will take it back from a diagonal back into a regular matrix. So, for example, if I said, hey, what if I, A is equal to S times 1, 0, 0, 0, 2, 0, 0, 0, 3 S inverse, and I say, I'd really like to know a to the 100th. Well, that would suck if you had to multiply a by itself 100 times, but instead, a to the 100th is going to be equal to s times the diagonal matrix to the 100th. And then you just put the powers inside. And you have saved yourself a whole crap load of calculations by doing that. If you could somehow figure out a way to turn A into this sort of similar to a diagonal matrix form, powers of A become very easy to compute. You still have a couple of matrix multiplications to do, but it's not so bad. It's not hundreds of matrix multiplications. So, if A was similar to a diagonal matrix, matrix powers are easy. All right, so let's go ahead and look at the differential equations version of this. Suppose, now we're getting to our second running example. Suppose that you're looking at x bar prime is equal to ax. And remember here, I'm thinking of this as x1 prime, x2 prime is equal to a11, a12, a21, a22 times x1, x2. That sucks. Those equations are coupled. We can't solve them. If A was similar to a diagonal matrix, if A could be written as S ds inverse, I guess in this case, let's just suppose that we have this specific equation, I don't know, 1002 S inverse or something like that. Doesn't really matter. Then what would happen to that differential equation? Well, the vector x prime would be equal to, okay, replace A with its diagonal similarity. Now, if you pull the S inverse to the other side by multiplying both sides on the left by S inverse, you end up with S inverse x is equal to, okay, well, S inverse times S is the identity matrix. Then you get the matrix D, and then I can collect these together as S inverse x. That looks an awful lot like a U substitution waiting to happen. I could just call the vector S inverse x y. So if I went here and I called this vector y, so y prime is equal to d times y. So here I'm just letting y be equal to S inverse of x. Well, that would give me an equation that I could solve by integrating. So I started with this problem that was hard, where the equations were coupled, and I cannot undo it by integration. And instead, I replaced it with a system of equations that looks like this. y1 prime, y2 prime is equal to this particular diagonalization I said, 1, 0, 0, 2, y1, y2. If I multiply that out, and either by observation or by using separation of variables, you could show that this means that y1 is equal to c1 e to the x, and y2 is equal to c2 e to the 2x. These are not coupled anymore. You can use this stuff from chapter 1 to solve these equations. Okay, well that gives me the vector y1, y2. Well, just like U substitution, I've used a substitution to turn this into a solvable problem, but it's not the problem I wanted to solve. The problem I want to solve was in terms of x. How can I get the x back again? Well, yeah, like if y is equal to S inverse x, then isn't x just equal to S times y? So that's how you fix it. You did the U substitution, you solve the problem, and then you substitute back. You did the U substitution step here, You solve the problem, and then you substitute back by saying, well, x must be equal to s times y. I'm giving you a heuristic here more than an actual example. We're gonna do some examples of this. Actually, we have diagonalization set up. So the idea is, if the matrix A was diagonalizable, I can manipulate the differential equation it's part of to act like a U substitution, and I can use chapter 1 methods to solve the differential equation. We will be concrete about this. So, the two big applications that we have, there are more than this, but for now, the running examples are powers of matrices and systems of linear equation, differential linear equations can be studied effectively in the case where the matrix, if I happened to know that A could be written in a diagonal form, that would be nice. Now, you might suspect that after you've spent 2 sections doing nothing but eigenvalues and eigenvectors, that they would be at play in this conversation. And in fact, the diagonalization of a matrix is built out of its eigenvalues and eigenvectors. But there have to be enough of them. That's right. That's the whole point of diagonalizable matrices is they're not the defective ones. If you can't diagonalize a matrix, it sucks so much you call it defective and throw it away. Unless you do chapter 7.6 and you learn about Jordan blocks. And I don't have time for that. Okay, so I'm going to give you an example of how this works, and then I'm going to write the theorem down that implements this. So I had a really nice matrix selected here. Some nice information all ready to go from 7.2. So an example that we went through last time was this matrix. So here's an example. This is an example of diagonalization. Because I want to show you what's happening before I formally define it. If we have the matrix A is equal to 3, minus 1, minus 5, minus 1. We did that example last time. And I start telling you about the eigenvalues and eigenvectors of this thing. If you calculate the eigenvalues, you're going to get an eigenvalue lambda 1 is equal to minus 2. And it had an eigenvector v1, which we found to be of the form 1, 5. Lambda 2 was an eigenvalue of 4. Its particular eigenvector was minus 1, 1. So the point of everything that we're doing here is I can construct a diagonal matrix D by forming a diagonal matrix from the eigenvalues of A. Minus 2, 0, 0, 4. And I can construct the matrix S by writing down the corresponding eigenvectors in the right places. The eigenvector for negative 2, in this case, is 1, 5. I should say an eigenvector is 1, 5. So in the column corresponding to where I put that negative 2, I'm going to put 1, 5. In the column corresponding to lambda 2, I'm going to put minus 1, 1. And the claim is that construction of diagonal matrix of eigenvalues and invertible matrix of eigenvectors gives me the relation that D is equal to S inverse AS. Or if you like, A is equal to S D S inverse. In the last class, I tried to do this example, but I reversed the order of S inverse, and it didn't work out. Okay, so again, what we're claiming here is a pretty big claim. First off, how do I know that this matrix is invertible? Well, you could take the easiest way is you calculate the determinant, right? So the determinant of this matrix is 5. Okay, it's 6. The determinant's 6, so it's an invertible matrix. So if you wanted to, you could write S inverse is equal to 1 over the determinant times switching the A and D elements and then negating the off diagonal elements. This is the inverse of A, B, C, D is dA minus B minus C divided by the determinant. And so what we're claiming here, it's sort of big claim, is that I could write the matrix 3 minus 1 minus 5 minus 1 as 1 minus 1 5 1 times the diagonal matrix minus 2 0 0 4 times the inverse matrix. So I guess I could make it 1/6 1/6 minus 5/6 and 1/6. So I can build a diagonalization out of the eigenstructure of the matrix A. It's sort of it's not quite canonical, but it's almost. What I mean by canonical is it's the way you should do it. Now, I want to emphasize here, I could have put these eigenvalues in any order I wanted. I could have chosen these matrices to be any eigenvectors that I wanted, as long as they were linearly independent. If I wanted to put the vector 2, 10 here, that would have been fine. I could do that. If I wanted to make this matrix have the 4 in this spot and the -2 here, I just would have flipped the order of the columns. All right, so to really drive this home, I'm going to state the theorem, and then we're going to do a couple more examples. All right, so the theorem looks like this. If A is n by n with eigenvalues lambda 1, lambda 2 out to lambda n, not necessarily distinct, which means they could be repeating. I just have to have a list of n numbers. Not necessarily distinct. The number of times a particular eigenvalue will appear in this list will be its algebraic multiplicity. And associated eigenvectors v1 through vn, if v1 through vn is a linearly independent set, then A is similar to a diagonal matrix D which is the diagonal matrix made of the eigenvalues so that is, we're saying D is equal to the diagonal matrix lambda 1, lambda 2, lambda 3, down to lambda n. And the matrix S is the matrix of eigenvectors that correspond to those eigenvalues. So all of this comes down to having enough linearly independent eigenvectors. If you have enough linearly independent eigenvectors, you can write a matrix as S, D, S inverse. That is given n linearly independent eigenvectors, A can be written as S, D, S inverse. If that's possible, we call A diagonalizable. Such matrices are diagonalizable. So a diagonalizable matrix basically boils down to, does it have enough different eigenvectors? And if it doesn't, then you chunk matrix. Until you do chapter 7.6, and then which we're not doing. Someday in your future, you might have to learn about Jordan blocks, but not here. Yep.
How does it work if you have two eigenvectors or one?
Can I show you an example?
Yeah.
Because the very next thing I was going to do is write one of these down. Oh, don't worry. I'm going to show you examples, and then you're going to just compute lots of them.
I was saying I'm glad it's not just me who asked the questions, but people just don't have
Okay, so if I give you this matrix, A is equal to 3, minus 1, 0, 0, 2, 0, minus 1, 1, 2. And you go through the process of finding its eigenstructure. What you'll find is that this matrix has eigenvalues. Lambda is equal to 2 with multiplicity 2. So the characteristic polynomial here, P of lambda, looks like minus 2 minus lambda times 2 minus lambda squared times lambda minus 3. So this has lambda is equal to 2 with multiplicity 2, and lambda is equal to 3 with multiplicity 1. I will also tell you that if you found the null spaces of the corresponding matrices, like you found the eigenspaces, what you would find here is that the eigenspace for lambda is equal to 2 is the span of the vectors 1, 1, 0 and 0, 0, 1. And the eigenspace for that eigenvalue is the span of the vector 1, 0, minus 1. So you do the work of producing eigenvalues and eigenvectors. This is the information you're looking at. What the algorithm tells us is I can pick a diagonal matrix to be built out of the eigenvalues of D in any way that I want, where what I'm thinking is the matrix D is going to have 2 copies of the 2 because it's multiplicity 2 and 1 copy of the 3. So I'll give you 2 different possibilities here. You could let D be equal to the matrix 2, 0, 0, 0, 2, 0, 0, 0, 3. That's one way of putting eigenvalues down the diagonal. But it wouldn't hurt anything if instead of diagonalizing it that way, maybe you want to put the big value first. Or, if you really just didn't want the 2's touching each other for some reason, you could choose this to be your diagonal matrix. It does not matter how you build this thing. Different fields have different standards for how they choose the diagonal matrix in a diagonalization. Okay, so what are the S's that go with this? In fact, the span does not have to be a certain order. You can put literally any vector associated with the eigenvalues any place you want. So there's a lot of choice. These are highly non-unique. So you could do 1, 1, 0, 0, 0, 1, 1, 0, minus 1. That would work, right? Yeah, so this is lambda is equal to 2. This goes with lambda equals 2. This goes with lambda is equal to 3. I just need the eigenvector columns to correspond to the eigenvalues that you chose. Whatever order you picked here forces an order on this. There has to be an eigenvector for lambda equals 2 here and here. However, I could also, if I wanted to, in some sort of alternative universe, I could have written 0, 0, 1, 1, 1, 0, 1, 0, minus 1. That also would work for S. It's still an eigenvector for lambda equals 2, a different eigenvector for lambda equals 2, and an eigenvector for lambda equals 3. It's really not unique. If you really, I'll show you some other ways this can go in the next example here. For this D, I would write S is equal to, well, I don't have any choices for the first column, except I don't necessarily need to use that specific eigenvector. I could use any multiple of it. If I wanted to, I could put 10, 0, minus 10 here. That's definitely an eigenvector for lambda is equal to 3 because it's a multiple of one I already know is an eigenvector. This means that you can always write this matrix down with no fractions in it if you really want to. Second column just has to be some eigenvector associated with lambda is equal to 2. So I could put 1, 1, 0 here and 0, 0, 1 there. That would work for an S. Lambda is equal to 3, lambda is equal to 2, lambda is equal to 2. As long as the vectors that you're choosing are linearly independent so that that matrix has to be invertible. If this is not invertible, all of this falls apart.
If you were to use the two, do they have to be the same multiplicity, like, or can you do them separately?
What do you mean?
The 1, 1, 0, and 0, 0, 1. Can you make one like 9, 9, 0,
Yeah.
and one like 0, 0, 6?
Yep.
Or they both have to be
Nope, any two linearly independent eigenvalue vectors will do it. Right? I could add them together. You don't want that one, I could put 1, 1, 1 right here. That would be fine too. Because that would still be an eigenvector because it would be a sum of eigenvectors. All right, so let me show you an example of where this doesn't work. And then we'll talk about why. And then next time we'll talk about applying this idea. So if I give you the matrix A is equal to 1, 1, 0, 1. We've done this example a couple of times already. And you calculate the eigenvector, the eigenvalues of this. So you write down the determinant of A minus lambda I is equal to 0, which gets you the determinant of 1 minus lambda, 1, 0, 1 minus lambda is equal to 0, which is the same thing as 1 minus lambda squared is equal to 0. Lambda is equal to 1 with multiplicity 2. And I'm going to emphasize here algebraic multiplicity. The multiplicity that comes from the characteristic polynomial. Yep.
Is it ever possible to have two free variables in one like 2 by 2 matrix?
Yes, in a 2 by 2 matrix, yes, actually.
Really?
Well, the identity matrix, which when you subtract away the 1, you just get 0, 0, 0, 0, which has two free variables.
How do you subtract away 1 in the identity matrix?
Okay, let me do this one and I'll show you. Okay, I'm going to give you the world's least interesting similarity when we do the identity matrix. All right, so if you study this one and then you say, okay, I'm going to find the eigenvectors, so you look at the null space of A minus 1i, then you're looking at the row reduced, there's your matrix, that's A minus 1i, you subtract 1s from the diagonal, and you augment that with zeros and you row reduce, oh, you're done. It's already row reduced for you. C1 is free. C2 is 0. So the solution set to this, which will be the eigenspace, right? The eigenvectors will come from solving this null space. You're going to get C1, C2 is equal to C1, 0, which is C1 times 1, 0. So you have one-dimensional eigenspace. The eigenspace is the span of one vector. So this has geometric multiplicity 1. Because the eigenspace is one-dimensional. It's the span of a single vector. So the problem with this exercise is when you go to try to diagonalize this, the matrix D is pretty easy to write. The diagonal matrix should be a diagonal matrix made of the eigenvalues with multiplicity included. So a list of two 1s. 1, 0, 0, 1. That always exists. Then you go and try to write the S matrix down. Okay, so S is supposed to be a matrix made up of linearly independent eigenvectors of associated with lambda is equal to 1. Well, there's one of them right there, 1, 0. Okay, well, what are you going to put in the second column?
2.
Oh, yeah, you could that would be in there because the scalar multiple of 1, 0 is definitely an eigenvector, but there's no other eigenvectors except for scalar multiples of this, right? If you try to put something here like 2, 0, this has determinant 0, which is not invertible, which means S inverse doesn't exist, and that means that matrix 1, 1, 0, 1 is not diagonalizable. there aren't enough linearly independent eigenvectors to make this matrix have an inverse. So this fails. If the algebraic multiplicity of any eigenvalue does not agree with its geometric multiplicity, there will not be enough eigenvectors to make an invertible matrix, and the matrix is defective. So yeah, then you get to write defective. Generally, people don't work with defective matrices if they can get away with not working with them. All right, are you ready for the lamest diagonalization of all time? I'm going to diagonalize a diagonal matrix. All right, so let's do exactly what we just did with the identity matrix. All right, I'm going to put this one on you. So, A is equal, oh, that's still illustrative. There's our original matrix. Let's calculate its characteristic polynomial. The determinant of A minus lambda I is equal to 0. That means the determinant of 1 minus lambda 0, 0, 1 minus lambda is equal to 0. So 1 minus lambda squared is equal to 0. So lambda is equal to 1 with multiplicity 2. Now, I'm going to compute the null space of A minus 1I. So if I take the identity matrix and I subtract the identity matrix from it, I get the matrix 0, 0, 0, 0, augmented with some zeros. Oh, they're both variables are free. C1 is free, and also C2 is free. C1 is free, C2 is free. And so that means the answer is C1, C2 is equal to C1 times 1, 0 plus C2 times 0, 1. All right, so let's write down what the diagonalization should be. What should the matrix D be? Let's see. 1, there's a lambda is equal to 1 with multiplicity 2, so there's those there, and then zeros everywhere else. Okay, S should be an eigenvalue corresponding to lambda is equal to 1, which is 1, 0. That's the V1. So this is V1 right here. So there's V1. And then there's another linearly independent eigenvector associated with lambda equal to 1. So I can put that in there. Here's 0, 1, which is V2. And now I'm making the claim, and I don't know, you guys have to tell me if you believe this, that the identity matrix 1, 0, 0, 1 is equal to this diagonal matrix times this matrix, which is the matrix of eigenvectors, times the inverse of that matrix. So I've diagonalized the identity matrix into 3 identity matrices multiplied by each other. So yeah, we did it. We turned a diagonal matrix into a diagonal matrix with a similarity transform that just left it alone. So yeah, generally,
You could have not used the identity matrix.
I could.
You could use 0, 1.
So in fact, if you start with any diagonal matrix, like if you start with something like 2, 0, 0, 3, and you run the same process we just did, you're going to find that when you do this, you're always going to end up conjugating by the identity matrix because it started as a diagonal matrix, right? So if it starts diagonal, you can just leave it alone. Yep.
How do you know that it works with eigenvalues?
So the reason, I just don't have time to prove that today. I can show you the argument for why it works, and it's, at least in the 2x2 case, because it makes it clear what's going on. The reason that it works is if two matrices are similar, they have to have the same characteristic polynomial. They have to. That's like you can just show directly that if two matrices have that S inverse thing, if A is equal to S inverse BS, then the determinant of A minus lambda I is equal to the determinant of S inverse BS minus lambda I. You can unwind the S inverses here. So determinants split over products. This turns out to be the determinant of S inverse times the determinant of B minus lambda I times the determinant of S. These are reciprocals of each other. The determinant of a matrix and the determinant of its inverse are reciprocal, so they cancel. And so the characteristic polynomial for B and the characteristic polynomial for A are the same. Right? So what that means, so if the characteristic polynomials have to be the same, what's the simplest matrix with the same characteristic polynomial as a matrix you started with? It's the one where there's just the eigenvalues are down the diagonal entry. Right? So that's basically like, so I'll do it in detail next time, but that's what's happening, right? Is that you're just saying, I can pick, if a matrix is going to be, like the simplest thing that a matrix could share a characteristic polynomial with is a diagonal matrix that has all of the roots for that characteristic polynomial down the diagonal.
The characters polynomial is like you're subbing into 1 or subbing into x, subbing into x.
Yeah.
Oh, okay.
And then the fact that it works for the eigenvectors is literally just like, you just write down the matrix multiplication and it falls out. It's like, it's magic. This should feel like magic that this works. There's no reason to believe that any of this should go, and the fact that it does means that this is one of the most useful ideas in basically all of math. Like taking matrices and pulling it apart into these diagonal pieces is used everywhere all the time. Even when a matrix isn't square. You could be, a statistician or somebody working in applied engineering, and you write down a problem and you say, damn, I'm working with a rectangular matrix and I'm trying to solve an equation ax equals b, and I can't diagonalize it because it's not even square. So then what you do is you just multiply both sides by the transpose of the matrix and you solve a different problem. That's guaranteed to be square. And it's also guaranteed to be diagonalizable. So I can start with something that I don't even have a square matrix. I can force it to be diagonalizable. And this, as weird as that looks, if you've ever taken a stat class and done a least squares regression or a best fit line, that's literally what this is. This is where least squares regression from statistics comes from, is this exact matrix calculation. So diagonalization is so powerful, even when we don't have it, we make it so we can diagonalize. All right, so next time we will do some applications. I'll show you how the differential equation things work. And then if I've got time, I will show you why Google got rich.
This is